Today I'm talking about how we're safely controlling an autonomous system with unknown dynamics. Consider this aircraft flying in an urban air environment. We can model this as a discrete time stochastic system with a known part of the dynamics, this unknown portion of the dynamics, which might be due to black box components in the autopilot, and sub-Gaussian process noise. Now the mission can be expressed as an LTLF specification, where we want to go to goal 1, go to goal 2, and always avoid this restricted airspace. Since this aircraft is in an urban environment around infrastructure and humans, we want to provide rigorous guarantees on accomplishing this mission safely. And this is really difficult to do as we don't know this part of the dynamics, so we don't know how the aircraft will evolve in time. We also need to account for wind and other vehicles in the environment. Now, in lieu of knowing these dynamics, we have an input-output data set that's generated by the system and the ability to collect more data. The challenges that we're addressing in this research is how to rigorously learn about this unknown component of the dynamics, quickly synthesize a control strategy, and then provide guarantees on this strategy of accomplishing this mission. In order to accomplish this, we build off of work that we presented at HSCC 2021, where we consider just the offline case. We use the static data set to perform Gaussian process regression and learn the unknown components of the dynamics. We use this regression to construct a finite state abstraction of the aircraft. We perform model checking on this abstraction to come up with this offline control strategy. This offline strategy then chooses actions given a current state of the aircraft that has a lower bound probability of satisfying the mission. Now the problem is that by just using the static data set, we might have a low probability lower bound, meaning we can't make any strong guarantees on satisfying the mission. So what motivates the online strategy is using the current state of the aircraft instead of an abstracted state of the aircraft, and also reasoning online about the abstraction. We define heuristics on the abstraction that involve not violating safety and advancing to certain accepting states in the abstraction. Now, we use these two current state and heuristics together in order to come up with an action that potentially has a higher lower bound probability of satisfying the mission. We also use new data to come up with a better regression and also perform refinement on the abstraction. Now, in doing so, we can start to think about doing safety critical control for complex missions for autonomous systems in very challenging environments. And preliminary results show that doing this offline then online approach improves the probability of accomplishing this mission when compared to just using the offline strategy.